My name is Hailun. I'm a third-year PhD student from Rutgers University, and today I will present our work AIRTAG towards automatic attack investigation by unsupervised learning with log text. This is a joint work with Rutgers University, UMass, as well as Yat-sen University. So cyber attacks are becoming more and more frequent. According to the report from Public Security, the number of cybercrime in 2021 increased by 600%. And the estimated annual damage is $6 trillion. Attack investigation is very important for understanding existing attacks as well as defending against the future attacks. Usually, the system will store the logs for security analysis, and when detect a malicious activity, such as a malware, the analyst will go back to check this malware and its related logs to discover the attack chain, which can find the attack sources as well as the attack damage. However, the traditional investigation method requires the experts to manually check massive log data, which can introduce much human effort. So to reduce the human work, learning-based attack investigation method has been proposed. The basic design intuition behind the learning-based method is that different attacks can actually share some common attack strategies that can be learned by some models, such as deep neural network. And as shown by existing work, there are around 200 common attack behavior patterns that can be learned. And if we can train a supervised model to learn it, we can identify the attack behaviors. ATLAS is one of the representative learning-based attack investigation work. Given the log files, ATLAS will first convert the logs into a provenance graph, which is also a common step in most of the attack investigation work. And in this provenance graph, the loads are the system subjects or objects, such as a process or a file. And the edges are the system events, such as a read or write operation. Then, given the attack clue as a start point, ATLAS will try to combine it with other loads and perform the binary classification to see if this node is also part of the attack chain. And if it is, ATLAS will add this node into the malicious node list. ATLAS continues this process until all the combinations of nodes are enumerated. And then it recovers the attack story by finding the edges and the nodes that are directly connected with the malicious node. And as shown in the right side, such classification is coarse-grained. So which means that when we misclassify a benign node as malicious, we basically misclassify all the benign behaviors that are connected with this node as malicious. Also, similarly, if we miss one attack load, we basically miss all the attack activities that are connected with this node. Also, the graph-based learning investigation methods suffer from some additional limitations. For example, the node classification is supervised task, which requires the data labels. And labeling such data can introduce much human work, and even worse, the humans can make mistakes when labeling the data. Also, existing work try to first convert the logs into the graph to reduce the difficulty of analysis. However, generating or operating on such graph is very time-consuming. And according to our experimental result, the graph operations can take over 96% of the total time. Also, the graph is abstracted data, which means that an application node in the graph can represent different status of the application. So such abstraction sometimes can bring inaccurate or unstable coarse-grained analysis result. And compared with the abstracted graph, logs sometimes can keep such fine-grained information better. Motivated by these challenges and because existing work try to first convert logs into the graph because the logs are too large and hard to understand. And recently, motivated by the recent improvements in large language model, we try to propose our method called AIRTAG, which directly performs the attack investigation at the log level with the help of large language models. More specifically, given the log files, we will first try to detect all the log entries that are potentially related to the attack chain. Then we try to reconstruct the attack story based on the detected log entries. And compared with graph-based method, we do not convert the logs into the provenance graph at the beginning, so we can reduce the overhead that caused by massive graph operations. And next, I will elaborate each step of our design. So, given the log files, we first do the preprocessing, which includes the formatting and tokenization. We merge these logs from different sources based on their timestamp. We also remove the useless information in logs. Such formatting is a standard processing in both Atlas and existing attack investigation work. Then we perform the tokenization. And unlike existing work, which try to tokenize the whole log file with some predefined and universal characters, we try to first detect the semantic fields and then split the values accordingly. The right figure shows some examples of our tokenization. For the passes, we use the slash character to split them. And for the IP addresses, we use the dot character to split them. Then we adapt the BERT model for embedding training. And more specifically, we customize the mask language modeling task and the next sentence prediction task. The mask language task can capture the causalities inside a log entry, and the next sentence prediction task can capture the causalities between the log entries. After getting all the embedding vectors, we perform the downstream task training, and we train a one-class classifier to detect all the log entries that are potentially related to the attack chain. More specifically, we train a one-class SVM model to fit most data's behavior, and it's actually based on the assumption that the attacker tends to use less frequent activities for the attack. So most of the log data should be benign. We can also train the model on a clean data set, which can bring better result. And when investigating the attacks, the one-class SVM model will try to detect each log entry and mark the outliers as malicious. We also provide several post-processing rules for such log entries that are marked as malicious to remove some of the false positives. But due to the time limit, I don't think I have time to discuss much details about this. So if you are interested, you can check the paper or we can get back it. And based on the detected log entries, we could generate the graph. We also scan the original logs to find entries that can connect individual disjoint graph components. And finally, return the whole graph. We evaluate our system on 16 log files, which cover 4 single-host attacks and 6 multiple-host attacks. We also evaluate our system on some on 3 log files that comes from deep impact datasets and 6 log files which cover 6 different failed attacks. When comparing the true positive rate results, we find that our method can be 16%. We can achieve 16% higher true positive rate. In terms of the false positive rate, we find that we can achieve 9% lower false positive rate. When comparing the time cost of our methods with existing work, we find that we could be 2 times faster. Our code and paper are now available, and if you are interested and want to know more details, please scan the QR code. Thank you. Next, I would like to take some questions.